In Chapter 4, we're going to focus on the atoms. Atoms are incredibly small, so small we can't even see them with a microscope, and yet they compose all of matter. We can think of atoms as the pieces of the elements, and the properties of the atoms determine the properties of the elements. There are about 91 elements found in nature, and over 20 have been made or synthesized in laboratories. Each atom or each element is unique. Different elements have atoms with different structures, and therefore different elements have different properties. In Western civilization, when the Greeks started thinking about matter, there were two differing opinions. One, that matter was infinitely divisible, and then others who believed that there was an ultimate particle upon which it can no longer be divided. And Democritus was one of the proponents of this atomic theory, and he said nothing exists except atoms and empty space. Everything else is opinion. But the Greeks didn't really have a way to test their theories or their ideas. Many years later, an English school teacher named Dalton came up with what he called his atomic theory. He believed that atoms were made of tiny indestructible particles, and he visualized these as hard indivisible spheres. And to this day, we still visualize atoms as spheres. He proposed that all atoms of an element are identical. Now we'll see that this isn't exactly true, but given the technology he had at the time, that's the conclusion that he came to. And what he stated was that in a given element, all the atoms are going to have the same mass, volume, and all their physical and chemical properties will be identical. Atoms of different elements will be different. So every carbon atom is identical to every other carbon atom, but carbon atoms will be different from sulfur atoms. Dalton was able to break apart compounds into their elements, and he was able to determine the mass of the elements that made up the compounds. And based on the ratio of masses of elements to one another in given compounds, he determined that atoms were unbreakable and they combine as whole atoms. He also said that the nature of the atom determines the ratios in which it combines, and we find that to be true to this day. And each molecule of a compound contains the exact same type and number of atoms. This is called the law of constant composition, and we see this in our chemical formulas. So for example, water always has 2 hydrogen atoms and 1 oxygen atom. And here is some modern evidence for atoms. We don't have microscopes, but we have things that are known as scanning electron microscopes. And what these do is these reflect back from the surface. This was something done about 20 years ago by some scientists in IBM, and they put some gold atoms on a silicon wafer, and they were able to use this electron scanning microscope to show that where the gold was, there were actual atoms, which could be considered to be atoms, these little bumps here. Now Dalton made up a relative scales for the atoms, and he based it on hydrogen. He said that hydrogen was 1 AMU, or atomic mass unit. Today we use the C12 atom, and I'll explain later what that C12 means, but there's a certain atom of carbon that we say is exactly 12 AMU. So the kilogram is defined by a hunk of metal in Paris, and in chemistry the AMU is defined by the mass of a carbon-12 atom. So AMU, atomic mass unit, is what we use to measure small masses such as atoms. Now we know today from our technology that atoms actually do have absolute sizes. For example, the mass of a hydrogen atom is 1.67 times 10 to the minus 24 grams, and the volume of a hydrogen atom is 2.1 times 10 to the minus 25 cubic centimeters, inconceivably small. Now I'm about to explain some of the experiments that showed the structure of the atom as we know it today, but before I do, we've got to go over some of the basics of positive and negatives. Anytime you have a positive and a negative charge, they're going to be attracted to one another. They're not really this color is just used to show you the difference. And like charges, positive and positive or negative and negative, will repel. Very similar to the same poles of a magnet. If you put a south pole to a south pole, it will repel, but if you put a south to a north pole on a magnet, they'll attract. And to be neutral, something must have equal number of positive and negative charges. These charges will cancel out. So understanding this is going to be key to understanding the experiments that I'm about to explain. Early in the 1900s, chemists known as J.J. Thomson in Cambridge and others proved that atoms had electrons, and they were able to figure out that electrons had very, very, very small mass, much smaller than the mass of the atom, and then electrons carry a negative charge. So they figured that the mass of an electron is almost 1/2000th the mass of a hydrogen atom. Now in chemistry, we say that electron has a -1 charge. Now what J.J. Thomson said is he believed that atoms were made up of this substance kind of like plum pudding. And plum pudding is a pudding with a lot of raisins in it, and the electrons would be the raisins. What he believed is the atom is breakable, unlike Dalton's statement that it was indestructible, and he believed that the atom structure were electrons suspended in a positively charged electric field. And it had to be positive because to balance the negative charge of the electrons. And up to that point, there was no experimental evidence of any positively charged matter. So Thomson assumed that there must be positively charged energy, this electric field. He also believed that the mass of the atom was due solely to the mass of the electrons, since the positive energy field would have no mass. And there would be a lot of electrons in an atom, and there would also be a lot of empty space, because electrons are negative and they're going to repel one another. So here's kind of a depiction of the plum pudding atom. This blue and this pink are the sphere of positive electricity, and the little red dots and little yellow dots would be the electrons that are kind of stuck in there. Now Rutherford was a student of J.J. Thomson, and in science you always want to prove that your theory, or you want to see if your theory can be disproved or remain viable. So Rutherford was trying to figure out how can you prove that the atom is empty? Is J.J. Thomson's theory or idea really correct? Well, if something goes through it very easily. So he thought, well, I'll use some large target atoms and I'll try and put something through them. So as the target atoms, he used gold. Gold has a high mass, it's very malleable, so they're able to get it in very, very, very thin sheets. So he used a gold foil. And gold presumably was made up of these atoms, and what he was going to shoot through these atoms, this bullet, was what was known as alpha particles. Now alpha particles are actually the nucleus of a helium atom, but they didn't know that at the time. They just knew that alpha particles were heavy and came from radioactive sources. So here is his experiment. He had a radioactive sample that shot out alpha particles. And these alpha particles should go right through the gold foil, because the gold foil is made up of these gold atoms that are mostly made of empty space. And the alpha atom should hit the other side here, and that would be seen by this fluorescent screen. Well, what he actually saw was most of the alpha particles went straight through, but some of the alpha particles were deflected, some at very high angles, which didn't fit the plum pudding model at all. The only way to adequately describe these results was to think that say that the atom had a very, very, very small nucleus that was positively charged, and it actually would still be mostly empty space, which is why most of the alpha particles would go through the atom, but then a few would be deflected and some shot back at very, very large angles. Some of them actually got shot back to the sample, the radioactive sample itself. So this is Rutherford's interpretation, what's called the nuclear model. It said that the atom contains a very tiny dense center, which he called the nucleus, and the amount of space taken up by the nucleus is about 1/10 trillionth of the total volume of the atom. The nucleus has essentially the entire mass of the atom. The electrons weigh so little that they contribute practically nothing to the mass. It's kind of like the contribution of your hair to your total body mass. He also determined that the nucleus was positively charged, and the amount of positive charge balances the negative charge of the electrons. Therefore, the number of electrons and protons would be the same, or, well, I'm getting ahead of myself. The amount of positive charge would balance the negative charge of the electrons. And that the electrons were dispersed in the empty space of the atom surrounding the nucleus like water droplets in a cloud.